SpaceX spent 7 full months completely overhauling the largest rocket ever built. What emerged from that downtime is the V3 architecture, a sweeping redesign of both the Starship and the ground systems holding it up. To get this towering vehicle off the ground, crews have to pump it full of super-chilled, cryogenic liquid propellant, and they have to do it fast before the sub-zero fuel boils off and evaporates away. The new loading system managed to top off the massive tanks in just 30 minutes. For context, NASA's Artemis rocket is smaller than Starship, but it takes their launch systems over 3 hours to complete the fueling process. Shaving that time down is essential for SpaceX to avoid fuel loss and eventually reach a cadence of multiple launches per day. The launchpad itself was rebuilt to handle the intense heat and pressure of the booster's thrust. Starship now sits on a reinforced concrete structure, equipped with a water deluge system built to absorb the shock waves from the engines. When the countdown hit 0, all 33 of the newly exposed Raptor V3 engines ignited simultaneously. Instead of the staggered startup seen on previous flights, the rocket launched in one continuous motion, climbing 25% faster than its predecessor. This initial phase of the flight confirmed that the reinforced ground infrastructure and the aerodynamic changes are capable of surviving the extreme stress of liftoff. 3 minutes into the flight, the vehicle encountered its most structurally demanding maneuver, hot staging. Instead of detaching and then igniting, the upper ship fires up its engines while it is still firmly attached to the lower booster. Those engines blast directly into a reinforced steel dome at the top of the booster. SpaceX relies on the internal pressure of the booster's fuel tanks to brace that dome against the intense exhaust gas, so the two stages can safely push apart. The vehicles cleanly separated, but the moment that connection ended, their flights took completely different paths. While the structural hull survived the separation blast, the ensuing minutes would test the limits of the new engine hardware, leading one vehicle toward a catastrophic breakup and the other toward a soft landing. After separation, the Super Heavy booster flipped around, preparing for a boostback burn to slow down and guide it back toward the launch site. To steer through the atmosphere, the booster relied on 3 newly redesigned grid fins, strategically placed to provide more control over the vehicle's descent. But the steering became irrelevant when the engines failed to relight. As the booster tried to ignite for the burn, the Raptors suffered a cascading flameout. Only 4 managed to fire, and they shut down almost immediately. Without the thrust required to brake, the booster spiraled out of control, building up heat and air pressure until it exploded in midair. This total loss of the booster means SpaceX's plan to catch a returning rocket with the launch tower's mechanical arms is effectively stalled until the relight process can be stabilized. Meanwhile, the upper stage ship continued its climb toward space, and just seconds after the hot stage separation, it suffered an identical problem. One of its 6 engines went completely dead. On previous V2 flights, a single engine loss often triggered a chain reaction that destroyed the entire ship. However, the V3 architecture features internal shielding designed to contain such failures, preventing the damage from spreading to the neighboring engines. The failure contained, the 5 remaining engines propelled the ship to 27,000 kilometers per hour. Once in space, it successfully tested its PEZ dispenser payload system, deploying 20 Starlink mass simulators. Then came the return. The ship plummeted back into the atmosphere, wrapped in superheated plasma. Unlike previous tests where the heat shield returned with missing or melted tiles, the V3 ship emerged from re-entry in remarkably clean condition. The vehicle steered itself through the lower atmosphere, relit 2 of its 3 center engines, and executed a controlled hover before splashing down into the Indian Ocean. This test demonstrated the new internal containment system allows the ship to finish its mission even after a mechanical failure that would have previously ended the flight. The booster's mid-air breakup and the ship's struggle for altitude both originated in the same hardware, the Raptor 3 engine. Flight 12 showed that while the ground systems, heat shields, and structural hull are maturing, the reliability of the engines remains a central obstacle to the program's operation. Until SpaceX can guarantee these engines will light and stay lit exactly when needed, they cannot attempt more complex maneuvers, like orbital refueling or docking 2 ships together. Reaching the Moon and Mars requires a system that can reliably ignite dozens of engines over the course of a mission.
a standard this test flight shows SpaceX hasn't reached yet.